Good day, everyone. In this presentation, we'll explore how fluid behaves under different flow conditions, focusing on pressure loss and friction. We'll walk through two practices 2, 10, 18, 29, and 30, which investigate how different pipe designs, valve types, and transition affect energy loss. Let's begin. Our goal is to understand how different flow conditions influence pressure and energy loss. By analyzing smooth and rough pipes, valves, and varying pipe shapes, we'll see how real-world systems lose energy, something very important for engineering applications. In practice 2, we compared a smooth and rough pipe to observe how texture affects friction. The results showed that as flow rate and velocity increase, the head loss also increases. The friction factor lambda slightly rises, especially in the rough pipe, due to greater resistance between the fluid and the surface. This confirms that surface roughness amplifies energy losses through turbulence. For practice 10, we tested a pipe with bends. As the velocity increased, both the head loss and the loss coefficient K also went up. This happens because when fluid changes direction, turbulence forms, creating additional resistance. So the sharper or more frequent the bends, the higher the energy loss. In practice 18, we studied how the gate valve impacts pressure loss. The head loss increased with the flow rate, but the coefficient K did not follow a straight trend. It peaked at moderate flow, then slightly decreased at higher rates. This means the valve's internal flow pattern changes, creating nonlinear energy behavior. In practice 29, we investigated flow through a narrowing. As the flow rate increased, pressure loss and head loss both rose, and the friction factor lambda slightly increased. The contraction caused turbulence and higher energy dissipation. This proves that sudden pipe reductions lead to significant pressure drop and turbulence zone. Here, in practice 30, the pipe was gradually widened. Compared to the narrowing, the head loss is smaller, showing that a smooth expansion helps reduce turbulence. Instead of chaotic swirls, the fluid adjusts gradually, conserving more energy. To process our data, we used Bernoulli's and Darcy's Weisbach equations. We computed pressure difference, friction factor, and the loss coefficient using these formulas. By substituting our measured head losses and flow velocities, we derived all lambda and k values you saw earlier. Sum it, Summing it all up, each component affects the flow differently. Roughness and sudden changes create turbulence, while smooth transitions allow steady flow. We can see a clear connection between flow design and energy efficiency. Our results followed Bernoulli's principle. As velocity increased, pressure dropped. Head losses came from friction and turbulence, and gradual designs performed much better, showing why real-life piping systems are built with smoother curves and transitions to save energy. The gate valve experiment shows that pressure loss rises with flow rate, but K peaks at moderate flow and drops at high rates, showing complex flow behavior inside the valve. The narrowing experiment revealed that while pressure loss rises with flow rate, the loss coefficient remains relatively stable. Proper narrowing reduces turbulence efficiently. In the gradual widening, pressure loss also rises, but turbulence decreases. This smooth transition supports better flow and is ideal for minimizing energy loss in design. So, in conclusion, our experiments show how every detail, from surface texture to shape, affects pressure and energy. Smooth and gradual designs ensure efficient flow, lower head loss, and energy savings. These insights are crucial for designing pipelines, HVAC systems, and hydraulic networks. Thank you so much for listening. We're Group 3 and I am Reka. And this has been our presentation on pressure loss and friction in fluid systems. See you next time, and remember, keep the flow smooth.